All right, 4 o'clock. Online world has now joined us. Welcome back to your favorite class. Yes, almost done, man. Only 2 of your favorite classes left. Dang, today and Thursday. And you got a test in which you'll all cry, except for one thing. You won't because you're going to kill it. Yes. All right, so announcements. Homework number 7 I posted, ungraded. It's on lamina failure. Make sure you take a look at that. There's going to be a problem on your final about that, so make sure you understand that material. Got questions for it? Office hours every day, 8 to 9:30. All right. Study guide also posted. That's kind of like the qualitative style study guide. So we'll have a review on that sometime next week, probably maybe like Tuesday night or something. I haven't quite decided. We'll see what happens. I might have to proctor an exam on Tuesday, so TBD. All right. Your final exam takes place next Thursday, 2 to 4 on Teams. 2 hours, be just like the other one, except longer format. The meme today. It's not really a meme. It's a question I posed to the audience. Some guy encased a hot dog full of ketchup and mustard in an epoxy block. Composite or not a composite? Elaborate. We had a lot of conversation before class on it. Will I have same office hours during finals week? Sure. Just for you, Kev. Otherwise, you can email me. We'll make an appointment. Composite or not a composite? Single continuous fiber composite. I like Ethan's mind. Put a hot dog in epoxy. There you go. Single fiber composite. I would say yes, right? You've got a matrix, obviously, which is the epoxy. You've got a reinforcement, which is a hot dog. Sort of a strange reinforcement, but it is. There's an interface that exists between the two. All right, this like mechanical interface that that exists between the two. The only debatable thing that you might bring to the table is, does it in some way have a benefit over its original constituents? So obviously the hot dog not going to taste as good anymore. So I don't know. That one's kind of going downhill. The epoxy probably not as good as it once was. So, but Chrissy makes a good point. It has an advantage in that you're preserving the hot dog for later. So, that is an advantage over the original, is that it's being protected. And that is one of the functions generally of an epoxy matrix, is to protect the reinforcement from its surroundings. So, yeah, I'm with Chrissy on this. I would say yes. So when I ask you on your final exam, is a hot dog encased in epoxy a composite? Now you know. So be on the lookout for that one. Maybe I'll ask that as extra credit. All right, let's pick up where we left off. Again, I hope the math pants are being worn today. All right. So last we left off, we were talking about how to determine the strain at an arbitrary point in the laminate. All right. I'm going to post your favorite picture here one more time. And it's a picture we've kind of like beaten to death in this particular class, but I'll put it up there one more time just because I think it's a nice figure and it kind of gives a good sort of picture of what's going on here. So we've got this plate that's going from a undeformed to a deformed condition. And we're more or less interested in what is the strain at this arbitrary point in space as we go from B to B prime. And we did a lot of stuff. I'm not going to revamp all the stuff. But more or less, we did a whole full derivation on the strain by determining what is the displacement at point B before and after the deformation in terms of the curvature and the extension of the laminate. And we came up with this general expression for the strain and kind of like this XY coordinate system. And we saw the following. That in our global XYZ coordinate system, we had something like the strain in the X, the strain in the Y, and the shear strain gamma XY was equal to the midplane strains, which we said here was epsilon X naught, epsilon Y naught, gamma XY naught. This is the midplane strains, plus the distance that your point is away from the midplane, that's this distance Z, multiplied by the curvature of the laminates in the various directions. We're using the variable kappa here. Kappa X, kappa Y, and kappa XY. Or we sort of had the following definitions for our midplane strains and curvatures. Here, this was partial U naught partial x. So how much I'm displacing per unit length in the x direction in the midplane. My strain in the y direction at the midplane is how much I'm displacing at the midplane in the y direction for every unit of advance in y. And a similar idea, my shear strain at the midplane, this is a combination of how much I'm advancing in x with every unit step in y, plus how much I'm displacing in y with every unit step in x. All right, so those are our midplane curvatures. Sorry, midplane strains. And then midplane curvature, or it's not really midplane curvature, it's just generally curvature. Was the following. We had kappa x here is negative partial squared w. So the second derivative of the displacement in the z direction with respect to x. So this is just a general curvature. You may have seen something that looks like this in your calc class. I don't know if you learn about curvatures in Calc 1 or Calc 2. You guys remember curvatures? I'm getting a lot of blank stares. Okay, I know that was like 3-4 years ago. So, okay. Curvature in the x, there you go. Curvature in the y, negative partial squared w on partial y squared. And this two-piece curvature, which is sort of like the curvature in shear, is partial squared w, and my two partial derivatives, partial x, partial y. All right, so these are my definitions that I'm going with. Okay, so that's generally the strain that occurs in a plate. Now, we haven't really talked at all about laminate. It's just generally for a plate. So now we got to look at sort of what's happening at the laminate when we have multiple layers of prepreg that we may have stacked on top of each other. Now we have some sort of expression for the strain and how that develops. So let's use that and let's develop an expression for the stress. So stress in laminated composites. Sort of the next section that we're getting into. This is sort of new material. We're not revamping any more material at this point. So remember that laminate is made up of many, many layers. So we've kind of like only like looked at a full plate, but we'll have to remember that in this class we talk about laminates as composites with many, many layers. Okay, so let's say that we have like a 4-layer laminate that looks something like this. So it's like layer 1, layer 2, layer 3, and layer 4. Okay. And let's say that I'm just at some arbitrary kth laminate. All right, so remember that we could describe any particular lamina of interest as the kth lamina. So let's investigate the kth lamina. Okay. So we know that any particular location inside of the laminate we can define with a variable z. All right, it's the distance above or below like this midplane of the laminate. We can use to define that location for like the kth layer with zk. Okay, we talked about that when we first defined how to find the laminate. So distance to kth layer in z direction is zk. So this allows us to sort of like define how far away from the center each particular lamina is in the stack, zk. All right, so why is this important? Well, if we know the general strain in the laminate from the kind of the definition we just did in the last lecture, we can use Hooke's law to define the stress. So Hooke's law defines stress in kth layer. And for now, we'll just do this in principal coordinates. Okay. Well, we know that this is something like stress 1, stress 2, stress 6 in layer K. I'll use the subscript K here. Is this Q matrix, Q11, Q12, 0, Q12, Q22, 0, 0, 0, Q66. This is my stiffness matrix for thin lamina multiplied by the strain in that particular layer. So here we'll have epsilon 1, epsilon 2, gamma 6. Specifically in the kth layer, right? So this is specifically Hooke's law in the kth layer and principal coordinates, right? But what I just derived previously was an expression for strain in the arbitrary XY coordinate system, all right? So remember that when we make laminates, the various layers inside the laminate might have various orientations of their fiber direction with the global XYZ coordinate system. All right, we talked about that when we talked about stacking sequence. If I made a laminate that's 0, plus 45, minus 45, 90, that means the first layer is oriented in the X direction, the second layer is plus 45 from that, the third layer minus 45, etc. Okay, so what I need to do is I need to transform the strains that I know in the XY coordinate system to the local coordinate system of each particular layer to determine the stress in that layer. Okay, so I'll say here, however, the 1, 2, 3 coordinate system of each layer has an orientation with respect to global X, Y, Z coordinate system at angle of theta k. Right? And we sort of talked about this. What is the orientation of the fibers in the kth layer with respect to the global XYZ coordinate system of the whole composite laminate? Right? So we can transform layer K from like its local material coordinate system into the global coordinate system by using transformation theory that we've talked about before. So let's transform what we know about the strains in the arbitrary or like the global coordinate system into the local coordinate system. Okay, so we're going to transform from 1, 2, 3 axes of layer K to global XYZ coordinates using our transformations. Okay, that's going to look something like this. The stress in the X, Y, and shear stress tau XY in the global XY coordinate system. All right, so these are specifically the stresses in XY and tau XY for layer K of interest here. One particular layer is going to be equal to my transformation matrix T in plane stress. And it might be a little bit more appropriate to say something like T with the variable of interest here at theta K inverse. My plane stress transformation matrix, so this is a 3x3, multiplied by Q for layer K, Okay, so it's my 3x3. Stiffness of this particular layer K. This is in material coordinates. So let's maybe make this a little bit more clear. I got to make this as clear as possible. All right. This is the stiffness of layer K and its principal coordinates. Here multiplied by T star for layer K. Okay, so this is again here like my Q bar matrix. Remember we talked about this? This is the stiffness matrix in the global XYZ coordinate system. All this multiplied by the strains that we know in the laminate. Epsilon X, epsilon Y, X, Y, layer K. Right? So remember that we called this the stiffness matrix in the global XYZ coordinate system for layer K. And remember we called this Q bar. It's usually how we denote it. Okay. So if we wanted to write this in a little bit shorter hand, we could write something like Q bar of layer K multiplied by strain X, strain Y, shear strain, gamma XY, layer K. All right. So this is kind of an intermediate Hooke's law that we sort of already kind of knew, but I'm just defining very specifically for one particular layer of interest. Okay. Where this is sort of like the stiffness matrix of layer K that has been rotated into the XYZ coordinate system so that we can sort of like do calculations appropriately. So here's the stress in XYZ of layer K. This is my transformed stiffness. And then this is strain in layer K. All right. But I have an expression for the strain in layer K that I can sort of expand on at this point. Okay. And specifically that substitution that we're going to do is that I know that the strain in layer K can be written using that distance away from the midplane ZK. And my previous definition of strain, which all the way back up here, is this. So all I'm going to do is more or less just put subscripts K on that definition of strain and see what pops out. So leave yourself some space here. This one's pretty tight. The stresses in the global coordinate system of layer K are going to be equal to this Q bar matrix of layer K multiplied by the expression that I have for the shear strain. And so remember that expression is something like the midplane strains plus the distance away from the midplane. We're calling this here ZK. Multiplied by the curvatures. Kappa X, kappa Y, kappa XY. Okay. I can distribute this. And you're left with kind of the shorthand version of this full relationship between the stresses that develop in layer K and the strains that we have in our laminate, given the stiffness of the individual layer K. So finally, in shorthand, after distributing, Q bar, you're going to end up with what we have here. This is the stress, usually written in this way, of layer K in the XY coordinate system. This will be equal to the rotated stiffness matrix Q bar in the XY coordinate system of layer K multiplied by the midplane strains of the laminate in the XY coordinate system. Notice there's no specification for layer K here because these midplane strains are just what's happening at the midplane. Plus your distance away from the middle, we call this ZB or ZK. Your distance away from the midplane, multiplied again by your stiffness matrix Q bar, XY, layer K, multiplied by the curvatures which develop kappa XY. Again, not specific for any layer K for the curvatures, because this is for the global plate itself. So here's your full relationship between the stress that develops in layer K and the strains that develop. Okay, so let's just, drive home each one of these terms. This is off axis. So global coordinate system, stress in layer K. This Q bar K term, this is off axis lamina stiffness. Layer K. This term here, this is the longitudinal midplane strains. Okay, so that's how much the laminate is sort of like expanding and contracting at the middle. This is your distance away from sort of the center of the laminate. So this here is distance of lamina K from midplane. This we've sort of already defined. And this guy here, this is the laminate curvatures. All right, exciting stuff. Plate theory. Yeah, baby. This looks complicated, but we're going to break it down. It's really not that bad. Right? We're going to MC hammer this thing. Break it down. Ho, ho, ho. Maybe I'm too old for him. I'm too old. You guys don't know MC. Do you guys know MC Hammer? Come on. What song? Don't stop. Hammer time. This is a beat you can't touch. Come on, you can't touch this? Oh my gosh. Parachute pants? God. I thought it was too obvious, says Lucas. Just like the derivation of strain in a plate. It's just very obvious. It's just obvious. Don't stop. Hammer time. All right. Yeah, we got a bunch of gobbledygook here. Sure. Fine. Let's put some physical meaning to all of this sort of stuff, okay? And let's actually look at what a stress distribution and a strain distribution in a lamina might actually look like. So this is stress and strain distribution in a laminate. We're going to do our best to sort of put a physical meaning to the equations that we just sort of drew. Okay. So remember an assumption that we made that strain is continuous through thickness. Right. And let's assume that we have a multiple layer laminate. Let's say that we have like a 09090 laminate. And let's investigate. 0, 90, 90, 0 laminate. With arbitrary load and moment. All right. So what do I mean by that? All right. Well, let's draw a picture because pictures are great. So here we have some side view of some laminate, X direction, Z direction. And let's say that we're going to load this particular guy. Going to put some tensile force in the X direction. And let's say we apply some bending moment, My, bending moment, My that's applied on this guy. And we know that we have a 09090 laminate, so we can sort of separate this into 4 layers. So this here is like a 0 layer, this is a 90 layer, this is a 90 layer, and this is a 0 layer. Okay. So we'll obviously get, what we're going to do is we're going to look at the strain and the stress distributions of the laminate. So for strain distribution, you're going to have something like Fx giving you a positive mid-plane strain in the X direction. All right, I'm pulling on this thing. So the mid-plane portion at the middle of the laminate is going to extend and strain in the X direction. I think that's pretty obvious to see. All right. The moment Y that you apply, this is going to give you some curvature, but basically we're going to have more strain at bottom and top, and it's going to be a linear distribution. Okay, so if I kind of had to draw these things, I might assume that, the force is going to give me some strain in the X direction that is sort of giving me something that looks like that. And from the moment, I'm going to get something that looks like this. Okay. Hopefully you're hearkening back to your 3005 days and remembering how loads and moments apply strains to your piece. So this is from moment. This is from load. All right, so let's draw what that distribution actually would look like on this particular piece. I'm going to blow this way up. I'm making music. Okay. So here's my composite. I'm looking at the 0, 90, 90, 0 layers. And I'm first going to look at the distribution of the strain. So let's say that this particular line represents some nominal strain in the x direction. This is maybe not the best figure here. I'm actually going to get additional tension on the bottom, so it's probably better to draw the arrows this direction. Yeah, it's probably a little bit better. Okay, so I get a lot of sort of like tensile forces on the bottom here. And on the top, I'm sort of like canceling out from the compression that comes from my moment. Come on, eraser. All right, I got compression on the top. All right, so my distribution is ultimately going to look something like this of my strain. Let's pretend that that's what my strain distribution looks like through this guy. Actually, let's do it the other way. Sorry, I'm kind of like giving you the run around here. All right. Okay, there you go. There's your strain distribution in the laminate. You have some constant value that comes from the load that's applied and some linear distribution that comes from the moment. Okay. So maybe my strain would look something like this. Now I have to consider like what the modulus in the x direction is for each one of these layers if I want to determine like what the stress is in each one of these layers. So let's make another figure here on this musical staff that represents like what is the modulus of layer x. Okay. If I know that I'm generally like loading in the 0-degree direction, my modulus will be very high. If I'm loading generally in the 90-degree orientation with respect to the fibers, my modulus will be relatively low. So if I'm loading with a 0-degree orientation, I'm loading like in the direction of the fibers for like, let's say this layer and this layer. And my modulus value will be the same for each one of these layers and will be quite high. Let's say that it has this value here. For the 90-degree layers, I know my modulus in the 2 direction is generally much smaller. So if I'm loading that laminate this direction, and laminate in layers, 2 and 3 here, these 90-degree layers, I'm loading in the 2 direction for those layers, my modulus is quite small in those general layers. So this here is sort of meant to represent some picture of what the relative magnitudes of the moduli in those various directions are, given the orientation of fibers with respect to the global coordinate system. I know if I load along the direction of the fibers, which these 0 degrees orientations would have, then I have different behavior than if I load across the fibers, which is like this 90-degree orientation. So my strain is continuous, and my modulus has like discrete jumps as I move through layers. And if we know that the stress in each one of the layers is like some Hooke's law version of modulus times strain, then ultimately I could come up with some expression for the stress in X that might sort of look something like this. All right. I have this general like linear distribution, but if we say here that the stress is something like the modulus in X times the strain in X, then I'm going to get some pretty like sort of funky distributions that are going on here. Okay. I can sort of take my 0 as like my baseline. So I see here that like the strain is 0 at like this location. So I know my stress will be 0 at this location. And the slope of the line of the stress is going to be shallow for this region, and it will be more aggressive for these outer regions here and here. Okay. So if I had to sort of like draw what the stress distribution might look like, I have like some minor compression here, and generally this slope will remain the same. And I have some like very aggressive stresses that occur up here. Oh, sorry. I wish I had like a fatter marker here. Okay, so this is supposed to represent the stress distribution in this laminate as you're moving through. Okay, so in these particular layers, like here and here, because the modulus is lower, but my strain distribution is still continuous, I have a generally like shallow slope here, where this slope is something like epsilon x ex for the 90-degree layer. But here, this slope, which is manifesting itself in sort of like the lower two layers, or the upper, the upper and lower layers. This slope here is something like epsilon x times the modulus and x of the 0-degree layers, right? So the idea here is when I go between like this layer here, which if we call layer number 1, and this layer here, which I call layer number 2, as I move across this interface, the strain distribution is not changing. I have continuous strain from layer to layer. But because the modulus in those general directions is different from layer to layer, as I move from like the 0 to the 90-degree layer, I have a jump discontinuity in my stress from layer to layer. Okay, so here we see right below that second layer, my stress is some value, and then right above that second layer, my stress is some other value. Okay, so strain distribution continuous. Right, the modulus values here, they jump from layer to layer, and that causes discontinuities. In the stress distribution. Okay. All right. I was hoping to get a little farther than this, but this is where we're going to have to stop. This is going to conclude the material for the course. We're going to stop with this particular figure. If you understand and know this figure, you'll be good through the exam. I'm not going to ask any kind of like complicated questions on the derivation of the laminate failure theory. I think it's a little bit crazy. I was hoping to get through a little bit more laminate theory, but it is what it is. So know up to this figure. I think this figure is an important one to describe how the stresses are discontinuous through the laminate. So you should know this figure, but everything past this, I won't ask you about. So that's going to be it for the course. We'll take it easy today. On Thursday, we're just going to kind of have a fun day. I will talk about composites in modern technology. So we'll talk about things like 3D printing of composites, self-healing composites, some cool stuff. All right, so maybe the first 30 minutes or so of the lecture on Thursday, we'll just kind of highlight some cool stuff that's going on in the world, and then the last 20 minutes of lecture, I'll give you time to do your instructor evaluations, so you can finally get back at me. Yes. All right. So that's it. Hope you enjoyed the material. That's it for today. That's going to be it for the material for the test on the final. Thank you for coming, and be safe. Go eat your epoxy hot dogs. Can't touch this. I'm gonna stop the recording and I'm gonna play Can't Touch.